Hi folks, and welcome back to Physics with Captain Rod, making this example here to provide you with a look at how angular momentum is applied. So in this example, we've got this bar here, which has an axis of rotation going through it. And then we've got this putty-like geometry here, which is 2 kilograms and moving at 5 meters per second in this made-up example. And what's going to happen is the putty is going to hit the bar, and we're going to assume that it sticks to it. So after the impact, this system is going to be rotating. Now, I'm going to draw a series of pictures here. They're going to be kind of crummy pictures, but here's the bar, here's the putty, here's the axis of rotation. Here's the momentum vector, mv, for the putty. Next picture. The putty is, I'm going to say, in the process of sticking to. I'm talking about the 100th or 1000th of a second that the impact takes place. This is going to be for the impulses, and I'll draw those here in a moment. And then third picture. Here's the bar, putty stuck to it, and the bar is now rotating. Now in this example, let's see, we're going to consider this an isolated system, meaning that there's no other effects to worry about. Like, picture this being horizontal, if you will. This is not a vertical problem or anything like this. Imagine this happening on a horizontal table or something like this, and we're only going to consider the interaction of these things together. Now, let's see. Question A, draw the impulse diagram during the impact time frame. That's this picture. And when the putty hits the beam, it is going to put a impulse on the beam in this direction, some sort of F delta T. Okay. By Newton's third law, there will also be a force on the putty in the opposite direction. Okay. This is an internal force and is not going to change the net momentum of the system. But usually when we're talking about impacts, I think even though those are internal forces, it's sometimes handy to have them in the diagrams anyway for at least the sake of discussion. But a very important thing to kind of realize about this problem is there is another external impulse acting on the system during the impact. All right, think about the contact point. The beam is contacted here by a pin. And during the impact, there's going to be an impulse this way. I'm going to call that like P for pin force times delta T. Okay? And this one right here is fairly important to realize that the linear momentum of this system is not conserved because this represents an external impulse acting on the system. So you cannot equate linear momentum in this system because the linear momentum on the left is not going to equal the linear momentum on the right because of that P delta T. However, notice that the net torque is 0. If you sum torques about the pin, the P delta T does not create any torque about the pin. And these animals create torque in the opposite direction. There's no net torque created by those animals either. So it's very important to realize there is no net torque on the system, which is why we can equate the angular momentum in this picture to the angular momentum in this picture. So while I'm at it here, I'm going to go ahead and write the angular momentum in the second picture as I2 times omega 2. Now in the second picture, our system, we got to remember though, is the bar and the putty. That needs to be taken into account in the moment of inertia, and I'm sure we'll be doing that here a little lower in the problem. So let's see. Draw the impulse diagram during the time frame. We did that. And we drew the momentum, angular momentum before and after. 2. Is there an external linear impulse? Yes, I discussed that. That that P delta T is an external linear impulse. Is momentum conserved? No, because of this. Okay. Is there an external torque about the axis of rotation? And I already discussed this. No, there is not. Is angular momentum conserved? Yes. Okay, now find the rotation rate of the system after impact. So I'm going to go up here and back to our picture to do the work. So here is picture 1. The angular momentum in picture 1 is going to be this momentum times this distance. So I'm going to go ahead and call that, let's see, how about the distance is half the length times mv, where the m is the mass of the putty and the v is the 5 meters per second. Okay? And now we can equate that to, because of the no net torque, the angular momentum in this picture. Now, the moment of inertia in the second picture. The bar with an axis through one end has a moment of inertia of 1/12 ml squared. I'll just use a bigger m for the bar. But the putty is also part of the system. So I'm going to tack on a little m for the putty times L/2 squared, because remember when you calculate moment of inertia, it's the sum of all the mr squareds. Right, so this now would represent the total moment of inertia of the system with the putty attached to it, times the new angular velocity, the angular velocity in picture 2. Now I'm not going to bore you with the numbers. Hopefully I did this right. I went through and crunched this before the video here, and I've got, for an omega 2, I got 0.5 radian per second. I'd like you folks to double check that and let me know how good I am with a calculator. Again, calculator work is not my strong point, but that's what I got when I ran all the numbers through this. See if there's any other questions here we need to talk about. What percentage of the kinetic energy was converted to thermal energy? All right, well, before the impact, the kinetic energy was due only to the putty. So that's going to be a 1/2 mv squared. And again, here you're going to use the putty, and here you're going to use the 5 meters per second. The final kinetic energy of the system is going to be 1/2 the moment of inertia. I'm just going to put I times omega 2 squared, right? Where the I is the moment of inertia of the bar, 1/12 ml squared, plus the moment of inertia of the putty. Put little m times L/2 squared. Then times the omega 2. I didn't actually crunch this, so I'm going to let you folks crunch this. So get a number for this, get a number for this. Now, the amount that got converted, right, is going to be the change in kinetic energy. You get that by taking your final kinetic energy, subtract your initial kinetic energy. KE final minus KE initial. That's going to give you a negative number because your initial kinetic energy is bigger than your final kinetic energy, or at least it should be. Then to actually answer the question, what percentage of the kinetic energy was converted to thermal energy? Take the difference in kinetic energy, divide by KE1, because that's how much kinetic energy we started with, times 100%. I'm going to leave this as an exercise to the viewer to get a value for that. And I hope that you enjoy the video. Have a great day.